SpaceX, you see here the booster successfully landed back on their drone ship after launch. And here you can see actually the footprint of the satellite. So the SL2 is stationed over Middle Africa, and so here you can see actually its central location, its nether position on the geostationary orbit, and this line here is indicating the operational footprint of the satellite. And as you can see, it's rather large. It spans half the planet. So you can use this satellite to communicate with people on this part of the planet, ranging from Iceland to Antarctica, from eastern Brazil to up to mainland China. So this is really a large footprint, and this makes it so attractive for the ham community to operate. So some details about some geometrical details. Here you can, for instance, see typical orientation of receiving antennas. So depending on where you are, you need to, of course, orient your antenna towards the satellite in terms of elevation and azimuth. Same as if you buy a satellite dish for television reception, you need to find the satellite you want to receive. So some examples here for central Germany, for instance. These are the so elevation 29 degrees. You need to tune it. And on the next page, you see a bit more of the extremes. Rio de Janeiro, eastern Brazil. You can see that the satellite signal is coming from quite a low elevation, of course, right? Okay. So some schematic of the actual payload. You see here a block diagram of the actual Oscar 100 payload with its receive and transmit branches, its traveling wave tube amplifiers. So I'm not going into too much detail. This requires some in-depth knowledge about RF technology, but please feel free to further dive into this into these details here. I'm going to skip a little bit through. So there is actually two different payloads on the satellite. It's a narrowband transponder and a wideband transponder. So today we will mostly deal with the narrowband transponder, as this is its key usage is to relay audio communication. There is also a wideband transponder which can be used for digital video. However, to operate this in this mode, you need quite an advanced ground station with lots of transmitting power, which I personally do not have installed here. But there's many folks that do this. But as I am only operating in audio only, we'll concentrate on this one. So this, what you see here, is quite important. This is the band plan of the transponder. In fact, it's actually not the latest version of the band plan. There has been a change in this, but you get the picture when you look at this. Basically, when you look at the frequencies, right? You're starting here at 2,400 megahertz. And 50 kilohertz, going up to 300 kilohertz. So this band here spans 250 kilohertz, which can be used by the amateur radio community. Now, there is people who are not too much familiar with different operating modes. CW, for instance, here is Morse. So you can operate in this band here using your Morse key. So this is it's a special operating mode. You need very little bandwidth to communicate with Morse code. But what's going to interest us today is the single sideband part of the band plan, which is this part here. Single sideband is a special operating mode for radios, which is very efficient. You only need a very small bandwidth for a single voice to transmit. So in this case, we are operating with about 2.7 kilohertz. which is about half the bandwidth as a usual telephone would have. Which also means that if you divide this band by 2.7 kilohertz, you can compute that the bandwidth is enough to host up to, let's say, 50 calls in parallel. Okay, let's see what's next. Okay, some numerical data here. There are some guidelines on how to operate the satellite. As you know, or may not know, if you are an amateur operator, you need to have a license. So everything that I will show you today requires a special amateur radio license. So you are not allowed to just start transmitting into the satellite because, first of all, you need to know what you're doing. You could even damage the satellite if you would use too much power or at least disturb ongoing communication. So you are obliged to closely follow the operating guidelines if you want to become operational on the satellite. But as I said, a license is mandatory, and to obtain licenses for amateur radio operations, you can take courses, online courses. You have to take a test. And then you will receive your license. There is different level of difficulty. Let's say there is a novice licensees and advanced licensees. Here in Germany, you can already operate the satellite with a novice license. So let's say for me, it took me, I don't know, 3-4 weeks to run through these multiple choice questions, and so with a little bit of technical background, it should be a cakewalk. All right, let's see. I'm gonna skip a little bit through some of these slides. So it's wideband transponder. So there's a little bit info about this SDR Control Center. It's located in Qatar, Doha. That's where the main payload is being operated. So the television transmitters. And the actual amateur part of the satellite is being managed by a German group of the AMSAT chapter Germany, and this is located in central Germany in Bochum. You can see some of the key personnel here and all the ground station. Looks really professional. I must say, I'm always impressed when I see these pictures. And this is all built on a voluntary basis, of course. So kudos to AMSAT Germany. So some pictures about the some press coverage. So and here's some detailed information on the ground segment for the SEL satellite in Germany. So I should say this is the ground station that is sort of managing the amateur payload. But all the amateur radio operators like myself, they do have their own ground station at home, potentially self-made. There's some. We don't cover this LiLAR. Okay, let's see. Skipping through a little bit. Of course, you're probably now interested on how do I build something like this myself. Okay, so let's fast forward a little bit. So here you can see a very, very easy setup to become operational. There are some price indications here on how much you need to invest for the individual components. Okay, let me just pause for a second here, just checking the feedback here. Okay, looks good. Okay, there's actually some people using the live chat feature rather than the Telegram group I can see here. Very interesting. Let me just go through these questions. So Michael is asking, since it's stationary, which continents is it accessible to? North America? This was already answered. Sorry, folks. Uh, the maximum region towards the west is eastern Brazil. So there's no access to North America, I'm afraid. I know that the amateur radio folks in the US, they are quite envying the Europeans for this nice piece of kit. And I know that there is activities going on to also install a geostationary ham radio satellite also above continental United States. So please be patient. We will get some coverage over to you guys at some point. Okay, cool. Back to these slides here. Yeah, so basically, how can I receive the satellite? All you need actually for receiving is a satellite dish, very cheap, 20 euros or something. I got mine for $8, which is a 100 centimeter dish up on the balcony, really cheap. This here is a standard LNB. You can buy in the shops for down to 2 euros or something like this. Maybe should invest a bit more, like, I don't know, 10 euros or so. You get a decent piece of equipment. Yeah, and then you need to feed the signal. This is for receiving the satellite, I should say, right? The transmission is a bit more complicated. We're coming to this. So for receiving, all you need basically is one of these very cheap software-defined radios, for instance, an RTL dongle. And here is another thing. This is a power T. Yeah, you need to supply 12 volts to the LNB. Depending on its polarization. So the satellite here we're using is using vertical operation, and for this we supply with 12 volts. So this can be built also from scrap components, or you can also buy this. You know, I did my early experiments with a very cheap coil and a capacitor. It works out of the box, very easy. So this is for supplying the LNB, and then you use this RTL dongle here and connect this to your computer. In order to really operate the dongle, you need a software, and there is a very nice software, open source freeware being produced by a gentleman called Simon Brown. It's called the SDR Console. This is a running project. It's constantly being updated and improved. This is a generic receiver software to operate software-defined radios. So you download this software, you do a little bit of configuration, and you're pretty much up and running. So you can already see here on the left-hand side, the reception is on X band, so 10.489 gigahertz. The LNB is doing a down conversion into the 700 megahertz area, and that's what the let me just go back one slide. So here is X-band reception. You do the down conversion inside this unit, and the RTL dongle is then receiving this in the 760 or so megahertz area region. So that's how easy you can get online on the satellite to receive the signal. Maybe I should say, for a matter of completeness, that you can even get even easier QRV or receptional by using a web service. Yeah, there is certain groups on the in the community who are actually transmitting the entire band into the internet and stream it into the internet. It's called a web SDR. I do not have the link here right now, but if you just browse, search for web SDR Oscar 100, you will find this very quickly. And then even folks in North America, well, anywhere with the internet reception, you can just play around a little bit and listen into the satellite. That's what I also did when I first heard about Oscar 100. So I played with the internet, and that was quite nice. But we want to really build something, and in order to be completely independent of the internet and work purely on the satellite, you need to start building yourself. Let me have a look here. So so here, Okay, there's a few more versions, and when you go through these slides, there's lots and lots of details on how to improve the setups. For instance, if you buy a commercial off-the-shelf LNB, which is designed for satellite for television reception, this is not, say, fully compliant with Oscar 100. There is frequency drifts, and you need to tweak this a little bit in order to get a stable reception. So for the folks who are who have a soldering iron and have a 20/20 vision, you can do stuff like this. You would replace the local oscillator of the LNB and replace this with a higher grade oscillator to remove any frequency drifts. There's other ways to optimize this, and I'll show you how I did this on my side. I did this with a pure software solution, and I did not have to make any modifications on my LNBs. Okay. Okay, let's continue. So AMSAT itself is also providing some kit for people who are not so keen on building for themselves. So here is a shop. You can go to them, and for a few €100 or so, you can buy equipment which is optimized for satellite operations. Different versions. They are really up to date. They are upgrading their designs constantly and improving. So a couple antennas. Here are a few examples on how antennas look like. This, for instance, here is a setup with a separate antenna for up and downlink. Typically, these types of antennas are quite beneficial as they have a huge gain. So these parabolic mirrors, they have very large gains. So you do not need a lot of output power. If you don't want to operate a dish for size reasons or so, you can also run a helix antenna. You can see this an example here. I think this is, I don't know, maybe a 40 winding helix antenna or so. There's other stuff like a typical Wi-Fi grid. Bear in mind, the uplink frequency is 2.4 gigahertz, which is Wi-Fi frequency. So you can use equipment which is, and repurpose equipment which is actually used for Wi-Fi, also for the satellite. So here are a few examples for feeds, in particular dual feeds. So you can already see here, when you look closely, this is actually the LNB, this part here, for reception. And for transmission, people have put the radiating element right on top of the LNB. So this is also the solution that I am using. I will show you in a minute. The nice thing about this is that you only need a single dish, because up and downlink go over the same satellite dish. There is, of course, it's a compromise. It's a compromise because, of course, you're shading the LNB a little bit with your radiating element, which means that the LNB is not as sensitive as it would be operating on alone. But let's say when you look at the power budget and the link budgets, that's fully tolerable. You may not be able to receive the weakest of stations, but say for typical operations, that's totally cool. As I said, the whole topic Oscar 100 is fully commercialized, guys. So you can buy almost everything. There's people trying to make money out of this, which is totally fine. There's other folks who prefer to build everything themselves. So you can choose. You can become very quickly operational by buying into your stuff, or you do some experiment, which is the latter I prefer, because it's a nice learning curve. You can see here some other kits. So you need an amplifier, of course, in order to boost your signal. There's different versions on how to do this. There's different companies that offer equipment from stock. go through this page here and look for what's available. Yeah, all-in-one solutions, you know. So real nice solutions. Of course, they come at a nice price tag. Yeah. So here, this now we're coming to a point, and this comes close to my setup actually. This is a more advanced software-defined radio. Remember, we've seen our first software-defined radio a couple slides further, this RTL stick, which was for reception only. This guy here can also transmit. Yeah? This is actually a evaluation kit from Analog Devices that hosts a software-defined radio transceiver chip. So this is used for all kinds of applications. I've seen so many people using this. This is used for Tesla, for instance. They are doing GPS spoofing experiments with this thing, and God knows what for. But also many amateur radio folks are using this thing to operate the Oscar 100 geostationary satellite. And with this, I want to go to actually my page, jump over to my page here. So this is the qrz.com page. Let me just quickly paste this page here on the Telegram. Okay, so this is like a Facebook for amateur radio people. So everybody can set up their homepage and write about their activities. Let me just quick check if there's any more questions on the other live stream. No. Good. Yeah, so you can see here stuff that I'm doing, and I have written an article about my Oscar 100 setup that I'm operating here. So this is an architecture of the system, a drawing of the system architecture. You recognize some of these terms. So here centrally, it's the Pluto SDR. This is it's this guy here. This is basically what I'm using, yeah, and you can see a few components around this. The nice thing about the setup is that you can hook this up to the internet and then operate your station, your ground station, from anywhere within the house. Yeah, so I have here an Ethernet. So all of this is basically built into a ruggedized aluminum box. I'll show you some pictures later. And it's a nice portable setup that I can also take on the road and take somewhere to do portable operations. Yeah, so you see here basically the up and the downlink. Yeah? So the uplink here goes through a high power amplifier. This is a 50 decibel, a 50 dB unit that can achieve up to 10 watts output power, which is more than sufficient. Yeah? So I'm actually throttling down to around 4 to 5 watts when I operate the satellite. When you look at the operating guidelines, there is certain limits. Yeah, so you must not exceed those limits, otherwise you could sort of damage the satellite-borne, space-borne hardware. And then on the downlink here, you can see, well, the LNB is outside, of course, but then you see the power T to provide power to the LNB attenuator, and then it goes back into the Pluto SDR. And all the magic is actually happening inside here. So if I scroll down a little bit, you can see here the actual Pluto. So I removed the casing and put this into a nice aluminum box, which I actually scrapped from other units. There are some modifications necessary to successfully operate this very evaluation kit. It's again related to frequency stabilization. So the oscillator on this board is not stable enough to operate Oscar 100 out of the box. So this needs to be replaced, and there's different ways on how to do this. If you read through my page, you can find some details. What I did was I removed the oscillator completely. was a bit difficult. Yeah, you need a hot air gun, and you need to be careful to not blow off other components here. But if you you can put some tape around it, some masking tape or so. But yeah, if you have a calm hand 20/20 vision or maybe a microscope, then with this is actually no problem. And what I'm doing is I'm feeding an external oscillator here from the outside. Yeah, you can see here this is actually a third signal that's running into the Pluto SDR to provide an external stable signal. These other two here are the RX and TX branches. If you scroll down, yeah, you can see here this aluminum box, and this is actually the SDR. You can see here a 10 megahertz oven controlled oscillator. So this is a very stable 10 megahertz frequency standard that I'm using. This was also from an old unit that I used. There is different ways on what you can use this for. There's folks using rubidium normals from old telecom base stations. Also, one very common thing to do is to use a GPS disciplined oscillator. So basically an oscillator that derives its frequency from the GPS satellites. They're a bit more expensive, but their advantage is that they are you switch them on and bam, you are operational. This guy here, it takes about 3 to 4 minutes to warm up and to stabilize. Yeah, here you see the power T to provide power to the LNB. So my unit here is actually, this is the lower level of the unit, and then on top, which you don't see here now, is the power section. Okay. Now let's jump to. So this is about the transceiver box. Yeah? So this is now nicely closed up and sitting out on the balcony in my setup, ready to become operational. Now I want to spend a few minutes to talk about the actual antenna. And here I've put quite some effort into, as you can see here, I've built this helix style antenna. Yeah? So this is a design I conceived last year in September before I became operational. I wanted to build an antenna which is mostly 3D printable and is easy to tune and and ruggedized so that you can operate it in the rain or snow or whatever. Yeah? So here in Germany, southern Germany, we have quite some severe snow sometimes, and also lots of thunderstorms and rain coming in. So it's important to have some kind of environmental protection for your gear. And so this is a drawing you can see here. This here on the far right hand side is the LNB. So this is the commercial off the shelf. And then you see a 3D printed base for the reflector. And here is a copper helix. It's a 3.5 turn helix. And this is how it looks like being put together. So these are renderings. And I show you, this is a 3D printed tool to wind the helix, so that you have an optimum pitch and optimum diameter for different wire diameters. Yeah, and here, this is how it looks like in reality. You can see this, it's printed mostly, it's all printed in PETG. You can see here after the rain shower, so it's fully waterproof, and I'm operating this type of design for a couple of months now. When you look at this page, you can download the design on Thingiverse, and you can build it yourself if you want to, or write me a mail, and I can help you out with printing. I have a few of these items here. So, for instance, let me now actually switch over to a different view. Okay, so you can see here some prints that I did. Yeah, so this is the cover. So this is printed from transparent PETG. And for the folks that are familiar with 3D printing, this is actually printed in vase mode. Yeah, so you can see here, it's actually really, it's just one single layer of filament. It's quite flexible, but very strong. Here's another one. Down here, this is actually, so it's only vase mode up until this level up. Actually, down here, it's pretty much solid because this has an inherent thread designed into it, so that you can actually screw this onto the reflector base plate. And so what I'm doing at the moment, I'm experimenting with different designs. So this one, for instance, is a taking 3D printing to the extreme. So this is actually a setup which is, let's say, 99% 3D printed. All the metal is only metal foils. So you see here the reflector is actually it's no longer an aluminum disc, rather a built from aluminum foil, and the radiating element here is just some copper strip. You need some special equipment to tune these types of antennas for optimum performance. Just winding the strip around and hoping it would work. This is in fact not the case. So you need you need at least to determine the standing wave ratio for this antenna to tune it properly. Otherwise, you would have too much reflected energy back into your transmitter. So you can see this here. So here is this is the base of the feed, an N-type connector, and you see here it's only a one turn helix actually, which works surprisingly well, I must say. So you can see it's quite a long one. I was just recently testing how the optimum number of windings. And I was removing more and more windings, and I surprisingly realized it still works with a single winding. Quite interesting. So, okay. Okay, good. So let's have a look to the clock here. It's 12:45 in Germany right now. So the session is we are 3/4 into the session, and maybe time for a quick summary. So I've talked about the amateur radio in general, and the satellite operations in particular. I've given you a little bit of an overview of how the AMSAT Germany actually realized this project, about its history, and some of the technology and techniques necessary and involved to operate satellite. So I must say, for me, this was really fascinating to dive into this, So I would say with an investment of a few €100 only, and maybe 100 hours in total, I was able to become operational on the satellite. So it's a project which is, say, not infinite. It's manageable. Okay. So let's just have a quick look back onto the slides. Let's see, is there anything else important to know? No, I pretty much through this here. Okay. So then let's get into the practical part of this session. We'd like to actually conduct some satellite operations. I was already on the satellite this morning for half an hour or so, and it may take a little bit of time until we get a response. I don't know how many people are operating at the moment, so it may hopefully we'll get some answers. After all, this is a live session, so bear with me if we have to be a little bit patient. Okay, right. So let's switch over to the SDR console. So you can see in the background now on the left-hand side a screen capture of the running console in the background. You see there's already something going on, and I will spend a minute or two to introduce you to the software. Just a second. Okay, right. So you can see here in the center the band of the satellite. I can zoom out a little bit to give you a bit of an overview. There are some markers here that, and these markers actually represent the band plan. So here is the far right hand side of the band, and if I move a little bit to the left here, you see the left hand side. You see part of the band which is reserved for CW, Morse code. You have some digital modes here, and then eventually the single sideband for audio. Yeah, and we see that there is stuff going on. So the waterfall diagram here shows you a two-dimensional view. So the horizontal, the vertical axis is time, and the horizontal axis is frequency. Yeah, so you can see also a little bit of the history of what was going on. Yeah, so and what else can you see here? Yeah, you see the frequency. So we are already tuned in to 10 gigahertz, 489 megahertz, 877 kilohertz. That's what I was using this morning. So this is the frequency that we will be using today as well. We may actually need to move a little bit to the left. There's one guy already operating quite close to it. So the radio is on mute, so I'll switch this on. And so maybe if somebody could just give me a quick heads up if you can hear something. So I have now actually tuned into the left side of the band, into the left beacon. So you hear a little bit of a beeping noise. I hope you can hear this. It would be quite important. But from what I see in the audio levels, you should be able to hear this. Okay. Yeah. So this signal. So what is? Let me just mute this for a second. What is the satellite doing? The satellite is actually receiving your transmissions from the ground, and the only thing it does is transverting this into X-band and relaying this back onto the ground, right? And it does this over a certain bandwidth. So these beacons you hear are actually beacons that are sent by the German ground station to the satellite, and the satellite is relaying them back. So and there are several of those beacons across the band. And they serve different purposes. For instance, they are actually used to calibrate the frequency. I am actually using these beacons here to calibrate my own ground station, because the beacons are running on a very, very precise frequency. So I know that this frequency is a certain frequency, right? And my LNB up on the balcony, which is not very stable, will drift in frequency. But the software, this clever piece of software by Simon Brown, has a feature that can track this offset relative to these known beacons. And that's the technique that's used to stabilize the frequency. So I do not need to make complicated modifications. I'm doing this on with a piece of software. Okay. All right, I'll switch on it again. Maybe take it down a little bit. So let's zoom out and let's see what's going on here on the satellite. Let's listen in to some of these ongoing conversations. Just a second. So I need to zoom in a little bit.
1,80 Spiegel und meine Ausgangsleistung ist 5 Watt von der Transceiver und es wird mit circa 50 Meter Kabel gedämpft.
Let me take this down a little bit. I've tuned into 740.1.
Also ich müsste ein bisschen dämpfen, ja, es kann schon sein.
And there is a German operator currently in a conversation with somebody else. So you can see here the bandwidth, the band. When I zoom in, it's actually a very nice modulation, very clean signal. Okay, here's the answer by somebody else. So when you look at the pattern, you can already see that this is a different station. Yeah, so the pattern looks somewhat different. Let's zoom out. There's more. Who's here?
Fragezeichen, Charlie, also das habe ich noch nicht ganz okay, zu schnell.
Okay, there's another German guy.
Auch noch nicht okay.
Here, over here.
Mit der Reparatur und ja,
the German
das jetzt ganz gut
talk going on. Yeah.
Ich benutze
Okay. Yeah, so you can see there's a bit of activity. So actually it's lunchtime right now. So many people are having lunch, at least in Central Europe. So it's interesting. Depending on the time of the day, there's different folks operating. Yeah. Nevertheless, I've been operating for a couple of months now, and I've talked to folks from Iceland to Antarctica, from Brazil to southwestern India. And it's really great. I really love it, I must say. Some people say, yeah, come on, it's so easy to operate the satellite. You know, there's not much tuning, not much. There's no ionospheric interferences and so forth. But anyways, it's really enjoyable. So what we're going to do now is we'll tune into our frequency and actually do some operations here ourselves. So let me, what was that, 877? So this is actually very close to an ongoing conversation. But anyway, it doesn't matter. So we'll just put ourselves right next to this one. Yeah, let's see if somebody answers. Okay. Testing, 1, 2, 3, testing.
Testing, 1, 2, 3, testing.
One more comment. You can see that we are hearing ourselves back. That's quite clear because all we're doing is we're sending up into the orbit, into the satellite, and it's basically relaying back on us. So we are hearing ourselves back. Okay, so I'm going to start. CQ satellite. CQ satellite. This is Delta November 8 Papa Alpha Tango. Special call for the virtual Maker Faire. Delta November 8 Papa Alpha Tango. Special call for the virtual Maker Faire. Calling and listening. Over. Okay. So you can see here this part of the waterfall was actually our call. Yeah. So we do an intro call. CQ, as the name suggests, means hello, I'm here, I want to talk to somebody. And people who are monitoring the band will see this and hopefully tune in to our signal and answer us. So as I said, we need to have a bit of patience and see and wait. Once people actually realize there's some interesting call going on, then they will all sort of pile up and rush into you. CQ satellite, this is Delta Oscar 8 Papa Alpha Tango. Correction, this is Delta November 8 Papa Alpha Tango. CQ Delta November 8 Papa Alpha Tango. A special call for the virtual Maker Faire. Delta November 8 Papa Alpha Tango. Calling and listening, over. Okay, I'm actually reading a few of your comments here. Thank you, Dragon Geek, that you can hear me. Great. Yeah. Pablo Martinez Diaz still using crystal radios. Science fiction for me. Yeah, it was science fiction for me too, but it got very real. CQ satellite, Delta November 8, Papa Alpha Tango. CQ satellite, this is Delta November 8, Papa Alpha Tango. This is a special call for the virtual maker fair. Special call for the virtual maker fair. Delta November 8, Papa Alpha Tango. Calling Oscar 100. CQ, this is Delta November 8, Papa Alpha Tango. Calling and listening, over. Yeah. Okay, actually we are very close to this other guy here. Actually, what I want to do is I move a little bit to the left, yeah, so that people can distinguish a bit better. So I'm moving to the 868. Okay. CQ, Delta November 8, Papa Alpha Tango. Sorry. Something. Just 1 second. CQ satellite. This is Delta November 8, Papa Alpha Tango. Special call for the virtual maker fair. CQ Delta November 8, Papa Alpha Tango. Special call for the virtual maker fair. CQ Delta November 8, Papa Alpha Tango. Calling and listening, over. So keep on doing this a few more times. Let's see. CQ satellite, Delta November 8, Papa Alpha Tango. This is a special call for the virtual maker fair. CQ, Delta November 8, Papa Alpha Tango. Calling Oscar 100. This is a special call for the virtual maker fair. CQ, Delta November 8, Papa Alpha Tango. Calling and listening, over. And we have to be patient. So, folks, I've actually exceeded the 1 hour of my session. So bear with me that this is a little bit